Hi, everyone. Thank you very much for attending to our talk. We're going to present the new concept of shadow vulnerabilities and how we applied it in order to attack the most famous projects in the world. So just before we begin, we're very happy to say that we are very proud to be part of this amazing community, the DEF CON community and the AppSec community for itself. And before we begin, just a really quick intro about ourselves. I'm the co-founder and CTO of Oligo Security. Like any other Israeli that you probably met, I'm ex-IDF technological unit, and in the last 8 years, I've been hacking and breaking software at Checkpoint Research. And I'm super famous for being handsome, or at least I think. And along with me is an awesome guy. He's one of our most talented researchers at Oligo research team. He's, again, like any other Israeli, ex-IDF technological unit, and he's been breaking and building software for all of his life. And he's very famous for being the best scuba instructor. He likes to deep dive into coral reefs and into complex bugs and code. So, just as a really quick agenda, what we're going to talk about today is the new concept of shadow vulnerabilities, what actually it means. And then we're going to give an example of a shadow vulnerability that we discovered in the famous Snake YAML Java parser. Then we're going to explain the process that we did in order to scale it and find vulnerable projects that are vulnerable to this shadow vulnerability. And in the end, like any good DEF CON talk, we're going to exploit some stuff and talk about the impact, and then sum it up with conclusion and key takeaways. So, just as like you might be familiar from this concept from other industries, the shadow IT, that stands for the IT, the infrastructure that we don't monitor, and hence we don't really know what's going on there, and hence there's a bigger risk of the stuff that we aren't aware of them. And you can see that this analogy goes in different world, the API world, the API that we don't monitor, and hence we don't know what's going on in there, the sensitive data, and of course, so on. And that's why we dubbed this concept of shadow vulnerability for exactly the same analogy for risks that we aren't aware of them, and hence they're even bigger to deal with and more riskier. And basically, shadow vulnerability stands for those type of vulnerabilities that actually doesn't get a CVE assigned to the issue. And why these things happen? It can happen for several different reasons. Of course, the most obvious one is that just takes a lot of time in order to classify, or there's a dispute between the maintainer and the reporter, and it might take a lot of time or even result in a no fix to get this issue a CVE. Again, there are a lot of examples in libraries and projects that just by not following the best security practices, you're actually opening a door for attacks. And of course, in the end, the maintainers that are responsible for the project are the ones that are deciding whether this issue is a real CVE or not, and they are the one that will flag it as a fix or not. And of course, what we're going to show that there are just libraries that are insecure by design, meaning that just by misusing this library, you're prone to a vulnerability. And again, the fact that we don't have a CVE associated, it's what keeps us blind, because all of the other tools or other approaches that we know up until now uses this CVE as the identifier to really understand where is the real risk and how can we deal with it. So now I'm going to pass it on to awesome guy that will deep dive and explain about how we found this vulnerable code pattern inside Snake YAML, and a guy can take it from here.
Thank you, Gal. Okay, so as Gal said, we're here to show you the new concept of shadow vulnerabilities. And to do that, we will dive into a specific example of a shadow vulnerability that we have found in a library called Snake YAML. So Snake YAML is a famous open source library for parsing YAML files in Java. It is ranked the #1 YAML parser in the Maven repository, and it is itself a dependency for more than 4,000 other open source packages. And just to recap, this is a YAML file. It is pretty similar to a JSON file, but it is meant to be more readable to humans. So if you are a human and you find this readable, so good for you. So let's say you are a Java developer and you want to deserialize a YAML file. I am a Java developer myself sometimes. Not proud of it, but yes, I am. What most developers will do, they will just try to find the first code snippet on the internet that works. So what they will do then, they will just find this snippet from the docs. They will copy and paste it to their code. They will try to run it, and it works. At this point, what most developers will do is will just close the docs and continue with their job. After all, there is no alert that you've done something bad. But if one digs a bit further into documentation, he will see this. Snake YAML allows you to construct a Java object of any type. So what is any type? Any type can be a string, an array, a hash map or a dictionary, and it can even be a custom Java object like this person class here. Trying to parsing this payload will result in calling the constructor method for the person class. But wait, any type? Something like this should really make your hacker spidey sense tingle. Can it even be a URL class loader? So just to recap, a URL class loader is a Java class that allows you to load the Java classes from remote servers, and basically it loads them into memory and it can also execute them. So apparently, yes, this also works. I'm sorry for the lame emojis from Windows. They used to be better. But yes, this actually works. If you will try to parse this YAML using Snake YAML, it will result in code execution from a remote server. As you can see here, the attacker control server. And I guess you wouldn't expect that just by parsing a YAML file, you will result in code execution, which can lead to complete takeover over the running host. So we were not the only ones who thought this was unexpected. This issue was reported a long time ago to the Snake YAML maintainers. As a reply, the maintainer said that, well, he doesn't see that as a problem. This is the intended behavior. Users who want to be safe can just use safe constructor. So let's pause for a second and explain what safe constructor is. So Snake YAML allows you to provide custom constructor types to configure the way that you control the YAML parsing. So for example, the safe constructor will only allow you to parse Java primitive types, such as a bool, string, int, and so on. And if it sees an unfamiliar type, it will just throw an exception and crash. There's also the constructor type, which will do exactly the same thing as the safe constructor, but instead of throwing an exception when it sees an unknown type, it will just try to parse it and to create any Java object that it can find in the class loader. And it's important to note that a part of the issue here is that the unsafe constructor, not the default constructor, is the default type for a Snake YAML. So if you will just try to initialize a new YAML parser, you will automatically receive the constructor type. It's you need to opt in if you want to use the safe constructor. And in order to make things even worse, constructor type inherits safe constructor, giving developers a false sense of safety when they're using the constructor type. I think this is the really root issue here, because developers who are using the unsafe constructor get a false sense of safety that they are using the safe constructor just because it inherits the safe constructor, but it actually overrides the safe behavior of the safe constructor. So is this a vulnerability? Well, you might as well say, yeah, this is not a vulnerability. It's up to the users to know how to use Snake YAML. the users need to read all the docs, and that's exactly the maintainer's point. But what we say is that this vulnerability is a source for so many other vulnerabilities that we have found that you might as well call this a vulnerability instead. It's important to note that the reason that we issue CVEs for open source libraries is to tell the users who are using these libraries that they have potential security issues. You need to notify the users that something that they are using can be dangerous. But because this did not get any CVE, we call this vulnerability a shadow vulnerability, since users who are using SnakeYAML will not know that they're using a possible vulnerable function. But anyway, all of this doesn't matter, since as the maintainer says, 100% of the applications who use SnakeYAML only use it to don't use it to parse untrusted input. We decided to test this claim. To do that, we introduced a concept we call reverse fuzzing. So if traditional fuzzing involves taking one target and shooting as many inputs at it, seeing when it breaks, reverse fuzzing is the process when you take one vulnerable code pattern, one vulnerable input, and throw it at as many targets as you can, trying to find the one that breaks. So the simplest way to start searching for targets in this process is to just search for the code pattern in GitHub. So we did do that, and we ended up with many results. And there were too many for us to just go through each and every one. So we had to lower the amount of false positives. We wanted to filter the targets by amount of stars to find only the prime targets. But sadly, the GitHub code search does not let you do that. So we had to write our own scripts to do this, and we had to run them for a couple of hours because of the rate limiting that the API has. But we did end up with much lower number of results. But still, out of all these results, we still had a few false positives because some of the projects that use SnakeYAML only use it to create YAML files and not to parse them. And also some of them are using the safe constructor. To eliminate the noise here, we just used CodeQL. For those of you who are not familiar, CodeQL is a powerful code querying tool that can help you find patterns exactly such as this. We ended up filtering the results, and we find a few prime targets. I will focus on a few of them now. So one project that we found vulnerable was Apache Cassandra. So Apache Cassandra uses the Cassandra YAML file to configure the server. Using the vulnerability that we have found, we've discovered that if a malicious attacker can control the contents of this configuration file, he can actually execute code on the running machine. And then we wanted to test, since this is a configuration file, we wanted to test if we can find an interesting attack vector for this. So usually attackers don't get the access to just edit configurations files on the servers. But during our research, we did find that on the default container image for Cassandra and the default installation, the Cassandra YAML file will usually have writable, write permissions from any user on the running host. So this can be leveraged to gain a local privilege escalation on the machine running Apache Cassandra. In addition to this, during our research, we have found another vulnerability in Apache Cassandra that did allow us to modify files on the Cassandra server. And then we just chained these two vulnerabilities together to obtain persistent RCE capabilities on Apache Cassandra. Another research that we started doing was also to search for more targets that are using Cassandra as a service, such as Amazon that is providing Cassandra as a service. Most of them really did sanitize the inputs, but the attack vector can still be valid for more services. So we did try to report this vulnerability to the Apache team that maintained Cassandra, and they were super responsive, and they immediately said that they do see the issue and they will issue a fix. But they did say that they don't consider this a vulnerability because of the attack vector, which actually created another shadow vulnerability because there is an issue, but it is not being notified to the users that it exists. And sadly, after deploying the fix, we see that they fell into the same pitfall that we mentioned earlier. They thought because the constructor inherits a safe constructor, they thought that just by using the constructor, they are safe because it inherits a safe constructor. But as we mentioned earlier, it overrides the safe behavior of the safe constructor. This is still left unfixed since it breaks some tests and stuff. So while we did found a local privilege escalation, and local privilege escalation is really cool, what we really wanted to find is a remote code execution, which is way cooler. And to do that, we had to expand our research to find even more targets. We did had some issues with the old method since not all the targets are open source. So searching GitHub limited the amount of results that we can get. And in addition to that, running CodeQL is pretty difficult in scale because you need to have the CodeQL database for each and every project. And as a maintainer already said, most of the projects do use SnakeYAML only for configurations. And we wanted to find a method how we can filter out those projects who use SnakeYAML only for configuration and find the ones who are using SnakeYAML to parse YAML files during their actual runtime. To do that, we decided to move from searching GitHub to searching for images in Docker Hub. We wanted to trace them in a runtime, and we wanted to plot the amount of calls that they do to parsing YAML files in order to find the ones who are not only using it in the beginning. Because what we understand is that when you use it for configuration, you usually only use it once when you start a container, and then you don't have to parse any YAML file. So there are a couple of ways of doing that. We wanted to do that in scale. And luckily, this is exactly what we at Oligo do. We use eBPF technology to observe the runtime behaviors of open source libraries down to the function level. And we do that at scale. So using the data that we had, we were able to plot these graphs on many popular projects. So this is an example for a project that was using SnakeYAML actually for configuration only. So you can see that over time you only see one peak at the beginning, and then there are no more usages. And contrary to this, this is a project that actually used it to parse YAML files on the fly. So these were the actually interesting targets. So using this method, we were able to find more targets. Some of them are still under responsible disclosure, so we can't explain the bugs we found there. But one of the targets that we did find, and we can show you here since it already got fixed, is Confluence. So just in short, Confluence is using another open source library which is called Liquibase that had this HTTP client code which was communicating with an API that was able to communicate and get YAML back from the API. So you can see here that it is not using the safe constructor, it is using the default unsafe constructor. So you can see here that once you issue a GET request, the output from the connection is being moved straight into the loaded function. So this issue was fixed in Confluent Server on the latest version, but it was not fixed as a security update. It was just pushed as a regular update. And there were many more projects that we found vulnerable to this. This vulnerability was kind of like a goldmine for us. Like everywhere we looked, we found flawed usages of this library. And to continue and sum up and give the conclusions, I will give the talk back to Gal.
Thank you, Guy, for being that awesome. Okay, cool. So let's sum it up. We actually were able to prove that vulnerability, not a vulnerability, but we were able to hack one of the most famous projects in the world. We started with an LPE, then we did a post-host RCE, and actually we did find a no-auth RCE, meaning that we have a huge list of IPs that are using this vulnerable code pattern that we can now take down, and this is still under responsible disclosure, but please stay tuned as we're going to publish it soon as we can. But now, let's see what happened. While we did our research, actually Google stepped in, and in one of the most famous tools, OSS which continuously fuzz the most famous open source project in the world for security vulnerabilities, and SnakeYAML is one of them, they did see that this issue occurs. So they open an issue. And of course, we already know our maintainer that just changed the status to won't fix. But then Google said, look, this is an RCE. We can actually run code. This is very severe. We don't agree with you. There was a dispute, and Google said, look, we are Google. We are a CNA. We're not going to ask you. We're going to issue a CVE. So in a return to that, the maintainer said, good, if you're Google and you can issue a CVE, you can come up with the fix to this problem. I'm not going to do it. And this is how we ended up getting SnakeYAML 2.0, which actually introduced breaking changes. It actually breaks the concept of deserializing structs and only lets you deserialize the primitive types. And by that, we still think that the world will remain vulnerable, because all of the other applications that are leveraging SnakeYAML for much more complex and extended usages beside the default types will have to use the vulnerable part. And now when you actually get to the official documentation of SnakeYAML, you can see right away the maintainer added, if you are here because of a CVE, it's probably a false positive. And again, as Guy mentioned, we usually trust the documentation that we read, and this is exactly the root cause of those shadow vulnerabilities, because if, without knowing all of that, I would just get into the documentation and see that there's a false positive, or say, okay, there isn't a risk. And of course, other projects saw this and followed, and for example, Apache Cassandra, that we did see that tried to fix it, but couldn't fix it. After this CVE applied, they just suppressed it and ignored it. Why? Because it would break in the builds of people, and people ignored. And again, they followed the maintainer's suggestion and just suppressed the vulnerability. So it's still out there. So this is actually raised an interesting ethical question. Who owns the responsibility? Is it the library maintainer that has been thankfully giving the world an amazing open source that let us build amazing tool, but now he needs to change the way that this code is worked just for others to use it safely? Or is it the project maintainer? They have thousands of open sources. They have to be responsible for each and every one's security? Or is it just the innocent users that just want to code and use a DB or use an open source and doesn't know or think about the consequences or the problems they inherit when they use it, or just the fact that they now have to be a Java security expert in order to just use a YAML parser. And as you can see, this is just the tip of the iceberg. This example of SnakeYAML is just one example of a shadow vulnerability, but there are many more out there. You can see the same documentation that are repeating itself from each and every example, whether it's like Lodash or Jackson, and you can see how the maintainers on one hand say, okay, this is not a problem, but on the other hand, you should be aware and be following the guidelines in order to use it safely, and we do see those stuff coming over and over in different use cases and different libraries that everyone are using. And there are many more out there. And that's why we urge you guys, we're going to publish a list of all of the shadow vulnerabilities, but we urge you to also participate and add more and more examples, because we think that it should be a security effort of all of the community in order to fix it. And again, like any good DEF CON talk, we have to exploit something. So I'm gonna pass it on to awesome guy that will show you an exploitation on Apache Cassandra with this shadow vulnerability.
So we don't trust the demo gods, so we had a video. So you can see on the lower terminal, this is the Apache Cassandra server. On the top one, it's the attacker. We have used two vulnerabilities that we are chained together. And once we reset the server, we can see that the malicious payload is being loaded. And we will get a connection. And we're now running as the Cassandra user.
Great, so.
You can upload now, yeah.
Great. Thank you, Guy, again for being so awesome. So now let's conclude what we have been seeing up until now. Open source, just like Guy, is awesome. And this is what enables us to build amazing application and do it. And on the contrary, because it's everywhere, that's why it's very important to secure those open source packages. And I think people even talk about Log4Shell or Spring4Shell or everything with shell, just keep recurring and showing us how important it is. And that's why we think, and by showing here the concept of shadow vulnerabilities, that the industry have to realize that fixing by a CVE cannot be the only focus. There are other problems out there, and that's why shadow vulnerabilities and these libraries that have this type of being insecure by design is just, again, the tip of the iceberg, and that's why this shadow concept should be called out. Because you saw that even if we have a fix or even if we have a CVE, a lot of the time it doesn't really solve the real issue. And that's why we don't think it's someone's responsibility. We think it's everyone's responsibility, because we are all using, knowingly or unknowingly, in these applications that are built upon this amazing open source project. And that's why we think it should be a community effort. And that's why we need your help in order to do it. So again, thank you very much for attending this talk. Please stay tuned, as we're going to publish more and more examples of shadow vulnerabilities, and going to publish the new project that we hacked. And of course, if you have any question, you can reach out via LinkedIn or Twitter or X or whatever Elon will decide to call it tomorrow morning. We will there and be happy to answer any question that you guys have. Thank you. Okay, any questions?
Sure. I have a question for Guy. Where does he like to dive?
Yeah.
Where do I like to dive? I'm from Israel, so I mainly dive in Eilat. But I've been all over the world, and wherever I get to and there's water, so I try to dive there. So.
And to memory corruptions.
Did Cassandra fix the other bug you found?
Yeah, we found several bugs in Cassandra. One of them was fixed and issued a CVE by itself. You can see it was a command injection, so it actually lets you run code, but we used it in this research in order to create a arbitrary file primitive in order to actually exploit the shadow vulnerability of SnakeYAML. But the shadow vulnerability of SnakeYAML, it's still unfixed.
Yes.
It's a great question. You can find our blog in Oligo official website. We're going to publish everything, like the research and how we did it. We're going to publish some tools and the way we did and scale the research. And of course, we're going to publish more and more examples of shadow vulnerabilities, so you can see it over there.
Yes.
but it's reading a bunch of documentation. And there's thousands of libraries. How do you go through everything and identify these shadow vulnerabilities?
Yeah, so that is a good question. Like, how do you find more shadow vulnerabilities in more libraries? What we wanted to do that is just focus on libraries that are actually doing dangerous stuff. So, like, deserialization is something that is known to be really dangerous. We didn't come up with a smart way to do like this at scale. But it's basically like focusing on the libraries that you know that can be dangerous and trying to find like these patterns of like documentation that says like it's your responsibility to do that and that in order to be secure.
Here comes the payload.
What? The payload? What payload we used? It was on the previous slide.
It's basically the URL class loader that will initiate a connection to our controlled server that will serve the malicious jar that will be executed.
This one, yeah. More questions? Yeah.
Tools under release, right? So are we expecting any open source to also find this kind of these vulnerabilities?
So yes, if we are planning to release an open source tool to find this. So currently not. It is based on the data that we have collected. But we can suggest that there is another way to search for this kind of issues using dynamic instrumentation. Like you can do the same thing with Frida, just in a less scale. Yeah. You only have what?
You only have data, so looking up the data endpoints can be shared. But
Yeah.
Cool. Thank you very much, guys. Thank you for attending. It was a pleasure to be here. And again, hit us up and we'd love to answer anything. Thank you very much.